Good morning, welcome back to Physics 4, Physics 4B lab. This week, what we are looking at is doing some measurements of specific heats of some metal samples. Now we've been looking at specific heat in class, and so this is, as promised, we're looking at a lab related to that. So we would like to go in today and do some measurements. We have a sample of aluminum. We have a sample of brass, and we have a sample of lead. And I'm going to be extra careful. I'm going to wash up good because I'm handling the lead. And the idea is this. The idea with this lab is to take each one of these metal samples. I guess the picture on the board looks more like the cube. So here's a cube of brass. And what we've got to do is get that up to a high temperature. So we're going to use a hot plate and some water. We're going to bring that water up to boiling, up to 100 Celsius, and we're going to place this inside, leave it in there for 5, 6, 7 minutes, let it reach equilibrium with the boiling water. And so this is going to be at a high temperature. Now what we've got in addition to that is we have what's called a calorimeter. Now calorimeter, I don't know if that's the best name for it, but the idea of a calorimeter is to create an isolated environment, an environment in which all of the heat inside is being exchanged just within the calorimeter. So the idea of at least an ideal calorimeter is that there is no heat going into the calorimeter from the environment or heat coming out. Now what our calorimeters look like is this. I've got a thermometer and a cork. I'm going to take that off, take off the lid. And our calorimeter has a couple of different aluminum cups. So what we've got here is, here's the inner cup, here is the outer cup. Now there's a piece of insulating material, some engineered something here. And the idea is we want to keep the inside cup thermally isolated from the outside cup. The outside cup, ideally, will remain at room temperature. The inside cup, we're going to put some water in here. So I'm going to put some water inside here, and then set this in place. Now, before I do that, I actually need to measure the mass of the inside cup, and I need to measure the mass of the water that I'm putting in. So I've got some scales here. And I can set this onto my scale. My scale says 56.9 grams. I'm going to write that down. And then I'm going to go and fill it with some water, maybe up to about here. And then I'm going to measure this again, because I want to know how much water is inside there. I want to know how many grams of water are in my calorimeter. So I'm going to place this inside. Now everything right now is at room temperature. And then what we can do is we can get a temperature on that. So we're going to need, need to get a thermometer. You need to get a thermometer in there and find out what the starting temperature is for the water and for the calorimeter. Now it's not enough just to say the thermometer's out in the room and that's room temperature. We want a thermometer right in with the water and with the calorimeter getting that measurement. So we are assuming that the inside calorimeter cup and the water are going to start off at the same temperature. Okay, so the thermometer is going to tell us that much. Now, we said that we're going to have a sample of some metal. In this case, it's this nice brass cube that you guys may have remembered from Physics 4A. And what I'm going to do is I'm going to transfer that in to the water, and quickly, because things are happening fast here, I'm bringing in this water that's like at 100 Celsius. And the water that's inside the calorimeter, maybe that's at 20 Celsius. And so the heat exchange is going to happen pretty quickly. Now, I want to make sure that when this sample of metal comes out, it goes right in and I get the top on it quickly. Okay. And the reason for that is the calorimeter now is, at least if it's ideal, which it turns out it's not, if the calorimeter is ideal, then the only heat exchange that can take place is between the sample the water, and this calorimeter cup. So I need to know the mass of all three of these, the water, the calorimeter, the metal sample. I need to know the starting temperatures. So I need to know what temperature the metal is starting at. Now that's going to be the temperature of the boiling water. That's going to be somewhere around 100 Celsius. And then I already got the starting temperatures here. Now once I place this inside, there's going to be heat transferring from the metal into the water, and I want the entire system now to reach equilibrium quickly. If I just leave it there all day, it's going to very slowly reach an equilibrium temperature, and during the time while I'm waiting, it could be that we're losing thermal energy to the environment, or you know, thermal energy is leaving, some of that heat is leaving. So we want this to happen fairly quickly. So to do that, we'll swish this around a bit. Now you got to be careful, because if you slosh it, you'll spill the water inside. And remember, we want the water to stay inside that calorimeter. All right, so that's the plan. That's what the transfer is going to look like. Let's take a look and see what the data tables, results tables will look like. Here is the metal sample. Here's our title and objective for the day. Here's the metal sample with its, I've got to get a mass measurement, temperature measurement to start with. Same thing with the water in the calorimeter, same thing with the calorimeter. Now notice the temperature of the calorimeter and water, when we start out, that's going to match. So some of these are kind of redundant. I guess I've written everything in to be as thorough as possible, but some of these numbers are going to match. And then there's only one final equilibrium temperature. So this should look like homework, right? Should look like some of your homework problems. Remember, I'm everybody's lab partner, and I'm a good lab partner because I've done all my reading, I've done all my homework, I am ready for this, and yes, this just feels like a homework problem to me. What we're going to do is start looking at how much heat transfer is taking place. So, and I'm just looking over at the hot plate here because I'm heating this in the meantime, and it's already boiling, so we're going to be ready to go over here in just a second. So I'm going to start measuring these different heats. Now, the heat that's going into the water, I can get by the mass of the water, specific heat of water, and the final equilibrium temperature minus the initial temperature. Now, all those things are measurable. So, and the specific heat of water, I'm going to look that up. We're going to treat that as a given value for the purposes of today's lab. Now, in the calorimeter, same thing. We're going to put in the values for the calorimeter, starting temperature, final temperature, mass, specific heat. We are going to assume it's aluminum and use the accepted value for aluminum for the specific heat of the calorimeter. And then I can add those two Q's together. This statement is saying that all the heat transfers that are taking place are within the calorimeter itself. None of the heat is leaving the calorimeter. No additional heat is entering the calorimeter. And then finally, we can come down and use our specific heat formula once more for the metal sample. And there we are. There is the specific heats. So here's what we're after. Now this is referred to, at least in the book, this is a mass specific heat, or just a specific heat. But we also want to get what's called the molar specific heat. In, I guess, chapter 19, we've been looking at specific heats and at molar specific heats. Sometimes we do this in terms of grams, sometimes we do this in terms of moles. And when we do this in terms of moles, it has the extra feature that often similar types of materials have the same specific molar specific heat. So for example, all metals have a molar specific heat that's about 3 times R. So we're going to write that down. There's a theory over here. Let me write that in. Where R is, R gets called the gas constant, but in lecture we've been pointing out the so-called gas constant R. applies to liquids and solids. It applies to all different phases. So we really need a new name for big R. We could call it big R. But in any case, we're going to be using that gas constant big R as a theoretical value. So that applies to all metals, the same way that the ideal gas law applies to all gases. Anyway, we want to do this specific heat in terms of grams and in terms of moles. Now remember, anything that's a delta T formula, we can use Celsius or kelvins. If we're looking at delta T formulas, they're going to be the same number. So I'm going to write this actually in terms of kelvins. You know, whenever I can, I like to work in terms of kelvins. It's a way to remind myself that those are the real absolute temperature units that we could be working in terms of. Now, to convert back and forth, we just need to know the molar masses. So we need to know the molar mass for aluminum, which we can look up, the molar mass for lead, which we can look up. Brass is a little more complicated because it's an alloy of copper and zinc. But I think I use a 60-40 formula. If I take 60% of the molar mass of copper, 60% or 40% the molar mass of zinc, and just add them together, that gives me a molar mass for brass. So that's what I'm going to work from. That should be in the notes on Canvas that I have for the lab. All right, the data table. Oh, this is the best data table ever. You know, it's always a challenge to see how many entries you can have in a data table. And I think this is going to, so far at least, this definitely is the most entries. What we have is we have, you know, let me take this back. This is wrong. So let me change this over. Let's say that we're looking at just one of the samples. Let's say it's aluminum. Because each one of these is going to have to be done 3 times. We're not going to just check the specific heat for aluminum once. We're going to do it 3 times. Or for brass, we're going to do that 3 times. So each sample, we're going to have to run through this 3 times. Now, we're going to need the mass of the water each time, mass of the calorimeter. That's not changing. So this could all stay the same. The mass of the sample should also stay the same. Okay, so I slipped those into the data table to get more columns. And then all the starting temperatures, final equilibrium temperature of everything. And then I think it's useful to calculate the Qs. So calculate the Qs, stare at the Qs. I think you'll learn something. You build familiarity. You build kind of an intuition in problem solving, in working with these materials. Now this is one of the dangers, and I know this happens out here. I try and watch for it in grading the lab reports. I know that sometimes people go, you make the data table and just send it out to everybody. That is a really bad idea. Because what happens is, by doing that, you don't get the learning experience of putting the data table together yourself. Okay. Now, when's that going to show up? Well, it's going to show up, it shows up in the lab reports to start with. Because what happens is, you know, somebody does a data table that makes no sense, and what I find is everybody in that lab group did a data table that looks just like the one that makes no sense. So, and you've missed out on learning that stuff. So on the midterms, midterms often will have a problem where it's related to something we did in lab. And if you didn't do the data tables, if you're unfamiliar with how these tables were put together, you know, you're not going to understand what's going on with those midterm problems. So make sure you are going through everything in the lab report on your own. Don't leave it up to somebody else to hand you a data table, a results table, a graph. Make sure you're doing all this stuff on your own. You understand how all this stuff works. That's an important, really important part of the course. So, we've got an aluminum sample. We're going to do 3 runs. We're going to get all this stuff filled in all the way across. We're going to get the specific heats and the molar specific heats. Then for results tables, we're going to have 2 different types. So there's a results table where we compared our measured value with accepted values. Now, accepted values are measurements that other people have done. So So in some sense, I want to say this is reality. So the reality, I guess that's not a good thing to write. I'm going to take that out too. Your stuff is real too. So this is reality based. But when we get over to the other data, the other results table, where we're looking at comparisons with theoretical values, theory is just theory. Okay, so theory is just theory. It's just, and in this case, the 3 R that we use here, although, you know, it's interesting to think about the theoretical foundation for that, it turns out that the reality is more complicated than the theory. So the theory gives us a really good estimate, but it's not highly precise. Anyway, we want to get both of these results tables. So you want to have a results table based on measured versus accepted, and then theoretical comparison between what you've measured and the theory. And we want percent differences on both of those. I think that's everything here. So that's everything on the board. I think what we can do now is we can, we can carry some of this stuff over. Maybe I can just continue here. Let's see where the sample go. I guess it's inside here. I'm going to walk over to this table, set some of this stuff up. And then I'm going to bring the camera over with us. So I'm going to come over to the lab table. So here's the lab table, and here is that boiling water that I told you about. And I got 2 thermometers in here, because I always like an extra thermometer. And the thermometers are reading about 101. Now, I'm always concerned that with, oh, there we go. Sorry about that. With the thermometers, they're a little higher because the bottom of the beaker is touching the hot plate. And so I am going to lift that above and see, and actually the value is coming back down a bit. Yeah, so it's coming down much closer to 100. See if it stays there or if it heads beyond that. Okay, that looks pretty good. So both thermometers in this case, and that doesn't happen very often, both thermometers were reading within a couple tenths of 100 Celsius. Ooh, there's a nice shot of boiling water. And so now what I want to do is I want to go back to, let's see if we can set this up so that we can keep an eye on these samples. I'll tip this just a bit where you can see the whole process taking place. And let me zoom in a little bit. All right, so what we want to do is, I got to go measure some water. Now I measured the calorimeter. I'm going to go put some water in this. I think we can do this all in one in real time. Okay, so I am putting the water onto the scale, 230.8, and I am going to put the water back into the calorimeter, and I am ready to make my transfer. I've got my thermometer here, so I'm going to need to get a thermometer reading for the water and the calorimeter that we're starting with. Let me grab a piece of paper and start writing some of these numbers down. So I've got the mass of the water, the mass of the calorimeter. I've got a starting temperature. I'm going to need a starting temperature. And the starting temperature is, oh my gosh, it's cold. It is at, I'm going to say the starting temperature here is 16.1 Celsius. Okay. Now, I had that combined mass that was 250.8. I had measured the mass of the calorimeter before. I think we're good to go here. So the process is going to work something like this. I need to transfer my sample from the boiling water. I'm going to turn down this heater a little bit because I think it's maybe a little over the top. I'm going to take this sample. I'm going to carefully put this in with the water. What I'm doing is I'm bringing my sample up to temperature. I want to make sure this is starting off at 100 Celsius. And then I've got the starting temperature on this. Take out my thermometer, take out the top. Now I want that to be ready to make the transfer. Now when I make the transfer, there's a couple things that I'm a little concerned about here. What I'm concerned about is the metal sample could be wet. It could be carrying high temperature water on its surface. If I stop and try and wipe that off, the metal's not going to be 100 Celsius anymore. I got to make this happen fast. I would like to remove some of the water along the way. So the method I'm going to try here is the bounce method. What I'm going to do is I'm going to take this sample, which I hope I can catch with this hook. I have done that. I'm going to lift it off the bottom just for, a bit so that it can reach equilibrium with the water. Turn the water back up a bit here because it's stopped bubbling. Okay. And then what I'm going to do is I'm going to bounce it into the calorimeter. And that's what this looks like. All right, into the calorimeter. Oh, I'm not sure. Oh. Okay. So everything's in the calorimeter now. The water here, I guess we can turn down. Turn that off for a bit. Now, the temperature that I'm seeing is just shooting up. Now, there's some real concerns I have here with this thermometer reading. Is it touching the metal? What I want is everything to reach equilibrium quickly. And so what I'm going to do is I'm going to swirl this around a bit. I'm going to lift the thermometer up so that it's not touching the metal exactly. What I'm seeing, though, is that the temperature is still climbing. One way you can check to see if you've reached equilibrium is kind of swirl this around and see if there's any change taking place. So now I've got it kind of stopping here. So I don't see a lot of variation taking place. I'm going to give it just a bit of time. It's at, right now it is at 25.3. Give it a little more time to swirl around. I don't see it going any higher when I swirl. Now what's going to happen over time is if I've really reached that equilibrium temperature, over time, it's going to radiate back out, and the heat's going to transfer back out into the room. And so if, as I swirl this, I never see it go above that 25.3. In fact, now I'm seeing it start to drop back down slowly. Okay, so I think it is the calorimeter beginning to lose heat. And so I'm going to write in that final equilibrium temperature. I'm going to use that 25.3 Celsius, and then I'm going to run back and check my masses, make sure that I got all the masses correct. So the whole process here is going to consist of 3 runs with the brass. That's what I'm using right now. I got to put that back into the, oh yeah, it's still boiling over here. The bubbles are just smaller. So I got to put that back into the 100 Celsius sample each time. I'm going to dump the water out in between runs, right? Because I want the water coming in to be at room temperature, maybe a little lower. I don't want the water already starting out hot. If it already starts out hot, there's a good chance I'll be losing thermal energy to the environment right from the get-go. So again, it's going to be 3 runs with the brass, and then I'll switch to the aluminum, 3 more runs, switch to the lead, 3 more runs, and we will end up with you know, 3 runs that we can take a look at, see how much variation we're seeing from one run to the next. And then we can also do an average. So I didn't show that on the board, but what we're going to want to do is average over those 3 runs and then report that in the results tables. All right. I hope that works. Questions on anything, stop by office hours, lab hours on Zoom, Conf for Zoom, and let's get any questions answered. All right.